Introduction to Nuclear Physics. Nuclear physics is a branch of physics that studies the constituents, structure, behavior, and interactions of atomic nuclei. It explores the properties of protons and neutrons, collectively called nucleons, and the forces that hold them together in the nucleus. This field has profound implications in energy production, medicine, astrophysics, and weapons technology. Key concepts are: 1. The atomic nucleus. The nucleus is the dense composed of protons positively charged and neutrons neutral. The number of protons defines the element atomic number, Z, while the total number of protons and neutrons is the mass number. Isotopes are variants of an element with the same number of protons but different numbers of neutrons. 2. Nuclear forces. The strong nuclear force binds nucleons together, overcoming the electrostatic repulsion between protons. It is a short-range force approximately 1 femtometer, 10 meters, and is much stronger than electromagnetism at this scale. 3. Nuclear stability and radioactivity. Not all nuclei are stable. Some undergo radioactive decay to reach a more stable configuration. Common types of decay: alpha decay alpha, emission of a helium nucleus He. Beta decay beta, conversion of a neutron into a proton beta or vice versa beta, emitting an electron, positron, and a neutrino. Gamma decay gamma, emission of high-energy photons as the nucleus releases excess energy. For nuclear reactions, fission, a heavy nucleus, for example, uranium-235 splits into smaller nuclei, releasing energy used in nuclear power plants and bombs. Fusion, light nuclei, for example, hydrogen isotopes combine to form heavier nuclei, for example, helium, releasing vast energy powers stars and hydrogen bombs. Potential future energy source. 5. Binding energy and mass energy equivalence. The binding energy is the energy needed to disassemble a nucleus into its individual nucleons. Einstein's equation equals mc explains the mass defect, the difference between the mass of a nucleus and the sum of its nucleons, which is converted into binding energy. Applications of nuclear physics. 1. Nuclear power. Controlled fission reactions generate electricity approximately equals 10% of global electricity. 2. Nuclear weapons. Uncontrolled fission, atomic bombs, or fusion hydrogen bombs releases massive destructive energy. 3. Medical applications. Radiotherapy uses radiation to treat cancer. Medical imaging. PET scans and X-rays. 4. Astrophysics explains stellar nucleosynthesis, how stars produce elements and supernovae. 5. Archaeology and geology. Radiocarbon dating CDK estimates the age of artifacts and fossils. Challenges and future directions. Nuclear waste management. Safe disposal of radioactive waste remains a critical issue. Fusion energy. Achieving sustainable, controlled fusion could provide clean, limitless energy. Quantum chromodynamics QCD. Research continues into the fundamental theory of strong interactions.